In today's video, we'll be talking about diffraction. After watching this video, you should be able to understand why light can be considered a wave and understand why light undergoes constructive and destructive interference. All right, let's get right to it. What the heck is diffraction? Well, we've been talking about this previously, but diffraction basically is the bending of waves around obstacles or the spreading of waves as they pass through an opening. So for instance, if you're in your bedroom and your mom, dad, or whoever it is you live with starts yelling at you to come and eat dinner or whatever the case may be, you can still hear their voice even though they can't directly see you. Okay, and that is called diffraction, basically the bending of the sound waves around corners and doors and that type of things. Well, does light do that too? The answer is yes, it does. Light also is actually able to diffract or bend around small openings, but this opening has to be much, much smaller for diffraction to occur for light waves. So, how can we change the amount of diffraction that light undergoes? Well, typically, the smaller the obstacle or the smaller the opening, okay, so if we have light waves traveling this direction in this picture, okay, and these blue lines are supposed to represent the waves. As they hit this barrier, there's a small opening right here, okay, and as they hit that opening, they what's called diffract, and they start coming out in a arced fashion, all right, so be going this way. So the smaller that opening and the longer the wavelength of the light, the greater the amount of diffraction that occurs. Okay, so there's a direct relationship between the smaller the obstacle, the longer the wavelength, the greater the diffraction. Okay? And when a wave is blocked by a small enough opening, this opening now actually acts as what's called a point source for a new wave. Okay, so it's kind of like this opening is almost in a way like at the beginning of a new light wave. Okay, it's the point where it all originates from. It's the point source of light. Okay, so that's how you can change the amount of diffraction that occurs in light. So here's just an example problem I could ask you. Which diagram below best illustrates the shape and direction of a series of wave fronts after they have passed through a small opening in a barrier? And I apologize, this picture isn't a little better. But we have picture one where light waves are coming from left to right and they hit this opening and then it's like they converge together. Okay. Picture two has again light waves going from left to right and then it looks like they converge together and the wave fronts almost appear to be going in the opposite direction. In picture three, we have light waves actually coming towards the opening from right to left and light going from left to right. Or we have picture four, which is actually the correct picture of what diffraction would look like. Light waves going from left to the right, they hit this opening and then it's like a point source for light expanding outwards from that point. Here's another example for you. A beam of monochromatic light, and monochromatic light basically means light that's just of one frequency. So a laser beam is kind of an example of monochromatic light. Approaches a barrier having four openings, A, B, C, and D. And I again apologize, this picture is so poor, but this one says that it has an opening of 0.2 millimeters, an opening of 0.3 millimeters, an opening of 0.4 millimeters, and an opening of 0.5 millimeters, okay, going from A, B, C, and D. Of different sizes as shown below. Which will have the greatest diffraction? Well, if you remember from our very first or second slide, we talked about that the smaller the opening, the greater the diffraction. And so it would certainly be A. This one with this really small opening would cause the most diffraction to happen from, say, this laser beam. If it was shot into both or all four of these different openings, opening A would cause the greatest amount of diffraction. So where we're going with this is basically when a laser beam is diffracted, the light acts as, again, a point source, right? And as that point source spreads outwards, you're going to get something called constructive and destructive interference from those point sources. Okay, and if this is a picture of an experiment that we're going to talk about in the next lesson, it's called Young's experiment. Basically, he shot, well, he didn't shoot a laser beam, he used the sun's light, but in class what we're going to do is we're going to use a laser beam, shoot it through a small slit, or a small opening, and then we're going to cause the light to diffract onto the wall. And if you look at the front of the wall, which is shown in this picture here, you'll see areas that have these red spots on it, then you'll see these areas that have black spots on it. The areas that are in red show constructive interference, meaning that basically two light waves have combined powers, if you will, and have showed up even brighter at that point on the wall. Okay, and that's constructive interference. Whereas the dark spots is actually an area of destructive interference, where two light waves have basically canceled each other out, and now you see no light there. Okay, and so this is kind of a cool experiment, and again, it was kind of to show the wave-like properties of light, that light is able to diffract, and again, it shows that light can be considered a wave. So there's actually a numbering system associated with these bands that will show up on the wall. And it may seem complex, and I know there's a lot of writing on this slide, but it's actually relatively easy once you get used to it. So the red bands of maximum brightness located at the center of the screen are ordered with whole numbers. Okay, so if we take a look at this spot right here, that is like the center point, and it's red, and that is 0. Working from 0, the next red band to the right or to the left would be called 1. And then if we go 2 bands to the right that are red, or 2 bands to the left that are red, that would be called 2, and so forth. So it's just whole numbers going from the center out. You go 1, 2, 3, 4, 5, and so forth. Okay, those are the numbers associated with those areas of constructive interference. The dark bands are assigned half number values. Okay, so from this middle point, wherever there's a dark band from the right and to the left, it's 0.5. Okay, and then I'm just gonna go from the left, it'd be 1.5, 2.5, and if there was a 3.5, it would be out here. And then same thing from the right, 0.5, 1.5, 2.5, and so forth. Okay, so it's just a numbering system that is assigned to these bands. And basically where those numbers fit in is in the next lesson, we're going to be talking about Young's equation, and this is going to be the M in his equation, is this banding pattern. All right, so that takes care of today's video. I will see you guys next time.